What does it mean, the mean value theorem? Have you ever heard that before? But we'll talk about this in a second. But what happens? What does the first derivative tell us? The slope. So what happens if we have two functions that have the same slope? How are they related? How are two functions that have the same derivative related? So to begin our journey there, we have to define something called Rolle's theorem. This is theorem 3. Suppose that y equals f of x is a continuous function over a closed interval and differentiable at every point on its interior. So what does that mean first? Suppose that y equals f of x. F of x is a continuous function over its closed interval and differentiable at every point on its interior. What does that all mean? What does continuous mean? It's a continuous function. What does that mean to us? What's that? Okay, but now with what we've discussed so far in class in the last 5 weeks, how do we know it's continuous? There's no breaks. That's if we have a picture, but I'm not going to give you a picture. I'm going to give you a function. What's that? And then what? It's continuous if 3 conditions exist. There's a value c that's the limit value of the function. F of c is that point. The limit exists at each point, and it goes to that c f of c value. Remember those 3 conditions? Has to be left and right. Limits have to exist on both sides. That value it's approaching has to be the same value f of c takes. That has to happen on each x value in that domain. Now, has to be differentiable at every interior point on this. Okay, why is this an open interval? And these are closed intervals. But why is this one closed or open interval? Right, because you can't differentiate A and B because the slope doesn't exist at a certain endpoint. So we need all the interior points because in order for a slope to exist, you have to be able to approach it from both 2 different sides. So it has to be differentiable, which means that we have to be able to take the derivative of each point. All right, so where were we? If we have this, if we have 2 points, f of A equals f of B, then there is at least one number C in the open interval AB, the interior point, such that f prime of C is equal to 0. This takes care of the constant function. So now we're looking at any other function. So here we have examples. Here's our function f of x. Here's A, and here's B. It's a continuous function. Check. All the points exist between A and B. It's differentiable. Yes, since it is continuous, it's differentiable at each point. Now, where is it not differentiable? What four conditions exist where it's not differentiable? If there's a discontinuity, this is continuous, okay. If it oscillates, this doesn't oscillate, okay. What are the last two conditions where it's differentiable? What conditions do we look for that's not differentiable? It's not differentiable at what? No. It's not differentiable at corners or cusps. In other words, if a function had a 90-degree corner, it's not differentiable, or if it's a cusp, it's not differentiable. So those are the four conditions: corners, cusps, discontinuities, and oscillations. Those are only four things we look for. Everything else it's continuous, it's differentiable. Because whenever you read a theorem, you have to look at what are the conditions that it's talking about. If f of A equals f of B, so here I have f of A, and here I have f of B. If f of A equals f of B, then there's at least one number C inside here where the first derivative equals 0. And that's what we'll be looking at. It's theorem 3, wasn't it? Yeah, that was theorem 3. So let's look at where theorem 3 would fail. Well, we talked about those. Discontinuity points, cusps, and or if the intervals don't exist. Let's look at example 1. Show f of x equals x cubed plus 3x plus 1 equals 0 has exactly one real solution. So how would we do that? How would we employ Rolle's theorem? Remember, that's what Rolle's theorem is stating for us. Suppose that f of x is continuous in a function, differentiable at a point. If f of a equals f of b, then there's at least one value c where the first derivative equals 0. If f of a equals f of b, Does f of a equal f of b anywhere? Can we find two x values where it's true? These are algebra questions. Okay, I mean, one way you could do it, you could take this equation, set it equal to 1, and see if it exists. Or no, we could think of another one. We talk about the intermediate value theorem. What does the intermediate value theorem tell us? The intermediate value theorem, in the grand scheme of things, it says if we have f of a does not equal f of b, then f of c, which are, it's a c is a point anywhere in the interval, can take on any value between f of a and f of b. That's what the main idea of the mean intermediate value theorem is. But take this one step further. If f of a and f of b have different signs, then there exists at least one c in a and b where f of c equals 0. Because if f of a is here, and b is up here, this is b and this is a, then there's at least one value c between there where it equals 0. That's the intermediate value theorem. So if we can find two values of x, plug those in there, and gives me different values, then I'm golden. What happens to f of 0? I always start with the easiest one. If f of 0, what do we get? Positive 1. I don't want to put positive. If I put positive x's, it's only going to give me more positive values. So that's not going to help me. So I'm going to go to the negative. What happens at negative 1? Is the answer going to be positive or negative? Negative what? Yeah, so negative 1 minus 3 plus 1. So we get negative 3. So now we have two different values. So that means there has to be an x-intercept, at least one x-intercept between 0 and negative 1. Now, the question is at exactly one real solution. The intermediate value theorem says, so there is at least one solution. In other words, x-intercept between x equals negative 1 and x equals 0. Now, how do we narrow it down to only one solution? If we take the first derivative of this function, it's x cubed plus 3x plus 1. If I take the first derivative, what do I get? What do we notice about this function? What do we notice about this? Can it ever equal 0? No, because if I move that over, it's negative, it's imaginary. So it doesn't have any vertices, and no matter what I put in there, it's always going to be what? Is it positive or negative? It's always positive. So this is positive, so it's increasing. Because it's increasing and it doesn't have a vertex, that means I can only have one and only one solution, or only one x-intercept. Which one we go? So that's how we use the intermediate value theorem and Rolle's theorem to start proving our answers. The mean value theorem, MVT. What the mean value theorem does for us, given any curve, it guarantees that parallel to any secant line, there is a tangent line parallel to it. So any secant line connecting A and B, here's A and here's B, there's a parallel line tangent to it, touching the curve at only one place. That's what it's telling us. We're going to be interested in finding that value. So that's the mean value theorem. That's not what it is. It's what it's looking for us. Looking for it to tell us. So here's the theorem. The mean value theorem. Suppose y equals f of x is continuous on a closed interval AB and differentiable on the interior of AB. What this first sentence tells us is there's no jumps. There's no discontinuities anywhere. It has to be continuous and it has to be differentiable, which means there can't be any points, any valleys, or anything like that. Then there is at least one point C in the closed interval AB, oh, interior points. C is an interior point, at which f of B minus f of A over B minus A equals f prime of C. Have we seen that before? The difference quotient. But what's missing to make the defined as a limit for us? X approaches C, right? Or 0, yes. We have to have a limit. But here what they're saying, we're now taking the first concept, because remember, what are we trying to prove here? What does this find? As opposed, what does this find? This is the slope of a curve between 2 points. This is the slope of a curve at a tangent point to the curve. So this is what we just discussed. This is the slope between points A and B, the secant. This is the secant, and this is the tangent line. We can take it one step further also. What does this thing prove for us? This is the average rate of change and now it's going to equal the instantaneous rate of change. And the proof itself is pretty straightforward, actually, by defining, starting with this, we just multiply both sides by b minus a and go from there. So let's look at an example of how this stuff works. You got it? Got it? Example 2. The function f of x equals x squared is continuous on 0, 2. And differentiable on 0, 2. Use the mean value theorem to find a value C in the closed interval 0, 2. So what's the graph going to look like of our function? We're only looking at 0 to 2 of x squared, so we only want this half of our curve. That's all we're going to want. So what is the mean value theorem? How do we use it to find the value C inside there? Remember, the mean value theorem says it's a continuous function, then there's at least one point C in which this is true. So what we have to do the mean value theorem, we got to find this slope and set it equal to the derivative. So we have to do f of b minus f of a over b minus a, which is f of 2 minus f of 0 over 2 minus 0. F of 2 is 4. So that's the average rate of change. So what this says, what this represents is the slope of this line equals 2. Now it's going to tell us that there's a slope, there's a point somewhere on this curve that has the same slope. So now we have to find the first derivative, which is 2x. Set them equal to each other. So f of b minus f of a over b minus a, f prime of c. This is 2, this is 2x. So this is c. So c is equal to 1. Whenever x equals 1, it will have the same slope as that curve. That's what it's telling us. Any questions so far? The hardest part is just the algebraic part. It's just do both slopes.
Sir,
Yes.
if you got C as 1, how did you get M equals 2?
I calculate this value equals 2. The derivative is 2c. I set it equal. I get c equals 1.
Oh, and that C value is that X value, correct?
It was the first derivative. This is the value I'm looking for. When x is 1, I plug that in there. I get 2.
Okay.
Mathematical consequences. These are corollaries to our theorems we just talked about. What this says is the question we're looking at: what kind of function has a 0 derivative over an interval? So what kind is that? You said it earlier. Constant functions. Because remember, it has to be 0 everywhere on the interval. Has a 0 derivative over the interval, not at a point inside the interval. When like a sine cosine function, they have 0 values in the interval or at the endpoints, but not throughout the entire interval. So that's what we're looking at here. Here are the corollaries we're going to look at. Corollary 1. If f prime of x is equal to 0 at each point x on an open interval, then f prime of, or f of x equals c for all x's in the interval AB. That's what we just talked about. So the next question we asked, what is the relationship between two functions that have the same derivative? Actually, the last example we just did answers this one. Corollary 2. If f prime of x equals g prime of x at each point x on the open interval AB, because they have to be interior points, then there exists a constant c, so constant value c, such that f of x equals g of x plus c for all x's in my open interval AB. Let's look at this as a picture. If f prime of x equals g prime of x, what does that mean? What does the derivative tell us? The slope. So if we have two slopes that are the same, if two slopes that are the same, then the only thing that's making them different in algebra, we said two lines are parallel if they have the same slope but different y-intercepts. Other than that, the rest of the equation is the same. They have the same slope. The only thing different to them is the y-intercept, which is your plus c. This is y equals mx plus b. This is y equals mx plus c. The only thing different is their y-intercepts. So let's look at an example here. Example 4. Find f of x whose derivative is sine x and whose graph crosses through the point 0, 2. All right. So the derivative, give me a function whose derivative is sine of x. Who's that? Negative cosine. Very good. Because its derivative is sine x. So therefore, there has to be another function that's different by some constant. So this function has to pass through the point 0, 2. So we have g of 0 has to equal negative cosine of 0 plus c. This has to equal 2. G of 0 has to equal 2. So what is cosine of 0? 1. 1 plus c, so it's negative 1 plus c equals 2. Add 1 to both sides. So the constant value is 3. So our function is g of x equals negative cosine x plus c, which becomes negative cosine x plus 3. Well, we'll finish up this tomorrow because we have one more problem to go through. Unless y'all want to finish it today. So I have one more problem. Let's go. Let's start to finish it today because that way we just go on to the next topic next time. This is a physics problem. What is it called? It's finding velocity, position, and acceleration. Here, where's the example? This is a free-falling body. Okay, let's see. Well, where's the question? Well, what do we know about free-falling bodies? They only have what force acting upon them? Gravity. Gravity is what kind of force? Is it position, velocity, or acceleration? It's acceleration. And it's a constant. It's 9.8 meters per second squared. Downwards. All right, so from acceleration, remember this acceleration is what? We started off with the position function. When we take the derivative of the position function, what do we get? We get velocity. To get acceleration, we take the first derivative of velocity. So acceleration is the first derivative of velocity. So if this is the first derivative of velocity, give me a function where the derivative of it equals this. Give me a function whose derivative equals that. Plus some constant. Because when I take the derivative of it, the constant disappears, the t disappears, we have that. So when we first dropped it, it's a free falling body, we start at 0, 0. So we start off with 0. So our constant function is 0. So that means our velocity function is 9.8 t. Doesn't have units to it. It's 9.8 meters per second times time. Okay, so that's the first one. The velocity is the first derivative of our position function. So give me a function whose derivative is that. So this is the derivative. Remember, we have a power. When I take the derivative, what has to happen? What should this power be? This should have been t squared. When I do the derivative, the 2 comes down, right? So I can't have 9.8. I have to multiply something by 2 to get 9.8. Plus some constant. But you always check it. 4.9 times 2 is 9.8. T, check. Derivative of this is 9.8. That's the acceleration. Check. So again, we started off at 0, 0. So the position function at 0, 4.90 squared plus c. S of 0 is 0 plus c. The y value is 0 equals c. So my position function is 4.9 t squared. The velocity function is 9.8 t. And the acceleration function is 9.8. Because it's a free-falling object, no other external force is acting upon it, started at free fall from the resting position. So this is how long, this is the values in which it'll hit the ground. Right, then the rest are laws of exponents and laws of logarithms. That's just algebra. We can go over that next time. And the beautiful thing about what we just did, this last example we just did, is getting us ready for the end of this chapter, or this one chapter here. We're starting looking at going backwards in mathematics. We're now looking at integrals, antiderivatives, going backwards from where we are now. Okay.